from. It's a pleasure to welcome Peter Lunts from Harvard University, who is going to tell us about the hybrid Monte Carlo techniques and auto-tuning for condensed matter theories in the first part of this morning lecture. And if you have any questions, feel free to interrupt at any time.
Okay. Hello. Is it working?
Yes.
Okay. Okay.
If the people in the online audience don't hear him, please tell us in the chat.
Yes. Okay. Thank you for coming, and thank you to Packer and company for inviting me. Yeah, today I'll be talking about this hybrid Monte Carlo with auto-tuning, which is a bit different than the hybrid Monte Carlo you might have heard of previously in this workshop. Yeah, I'm at Harvard, but I put Flatiron Institute because all of our computation is done at Flatiron. We're very grateful to the cluster center there. I'm sorry, to click on the slides. Okay. Yeah, so this is the outline of my my talk for day one. Yeah, I'll just introduce kind of the basic concepts and then go through the basics of HMC and then talk about the efficiency of sampling HMC and all the hyperparameters. And then second day, I'll talk about how to actually measure fermionic correlators in HMC, which is a little bit more tricky than usual, than normally is in the BSS algorithm. And then I'll talk about the details, some details of the bottleneck of the method, which is the matrix inversion. And then I'll talk about some generic issues that pop up and that we're addressing right now with more advances. Okay, so first of all, what these lectures are about. So just as a baseline, I'm going to be discussing methods for electronic lattice models at finite temperature. And I'm only going to be talking about models that are intrinsically sign problem free. And what I'll be discussing is hybrid Monte Carlo with auto-tuning as an alternative method to the BSS algorithm with whatever sampling strategies you want. So the main references for my talk are going to be mainly this paper, the first one, where we developed this method, and then the second and third paper, which the second one should appear very soon, is where we made further developments on this accelerating the matrix inversion, which is the computational bottleneck for each step of the algorithm. And the third one is more about more details about that. Okay, so as a first point, why would you want to look beyond the BSS algorithm? The BSS being this the main workhorse of DQMC. So so we're on the same page. So if you have some fermionic observable or some fermionic or bosonic observable O, then the expectation value here is defined with the integral over some Hubbard-Suchanovich field phi. And as usual, if as we all learned here in this workshop, the fermions can be integrated out to have some at the expense of some determinant D, which depends on the configuration of your Hubbard-Suchanovich field phi. And this D matrix in general has some dimensions of
I mean, it still shows on Zoom.
so I'll continue.
No. I mean, since for people with bad eyes, it's better. It's Zoom is actually very useful. You know. But I'm holding. No, it's back on. It's on. No. Yeah.
Okay. Can I continue?
Yeah, sure.
Yeah, okay. So this fermion matrix in its raw form has this sparse block structure, has dimensions beta, where beta is the inverse temperature, or rather the number of time slices that you discretize in inverse temperature, times the lattice volume. So L to the D, where D is your dimension. And yeah, so it has this form. If where these blocks here are all labeled by the time index, and so these are sign problem-free models. So here in this case, I'm only going to be considering the cases where this fermion object is positive definite. This determinant is positive definite. And in general, when you run this BSS algorithm, you compute this determinant exactly for every configuration of your Hubbard-Suttonich field over which your Monte Carlo is running. And this has a fixed minimum scaling cost. So when you do this expression, you use this expression that you learn here or elsewhere. This has a fixed scaling cost of beta volume cubed. So if you're in D dimensions, it's L to the 3D. This is not, there's some exceptions, like if your density is very low, which was worked out by Shiwei and company. But if that's not the case, then generically this is the scaling. And the scaling with volume is particularly brutal. And additionally, it's not just computational cost, it's also memory requirements. If you want to, in this method, you have to keep track of the inverse of this D matrix, which is dense. And for system sizes that I'll be talking about, this is many terabytes that you need to keep in RAM, which is not really feasible. So that's why, so we're gonna look for some alternative, which does exist. And also the idea is, if you're creating some toy models that are sign problem free, you're likely creating them to study some universal phenomena, like IR properties near phase transitions. And these phenomena are only visible at large system sizes. So it's very important to have a method that can address this issue and have a better scaling with system size. Okay, so for that, we're going to use HMC, and specifically HMC with pseudofermions. This is kind of the main point. This is different from the HMC that Johannes might have talked about. So the first point, the main the thing that helps us beat the scaling with system size is that we're not going to compute the fermion determinant exactly. We're going to compute it stochastically, which means that we're going to use this expression. We're just going to re-exponentiate the determinant. But now, sorry about this. This is a typo. This should be var phi and var phi star. So this boson, this field var phi is a boson. It's called a pseudofermion for historical reasons. And this identity is true when not only this determinant is a positive definite number, but this matrix D is a positive definite matrix. Okay, so that's not necessarily the case, and I'll go through that in a second about when this does not happen. And the nice thing here is that the calculation of the inverse of a sparse matrix does not really care about its size that much. It's much more interested in something called the condition number, which is like the ratio of the largest to the smallest eigenvalues. And so this is the key to beating the minimal scaling. Of the exact determinant calculation in the BSS algorithm. Sorry.
The reform the technician these days, they need to know us very well because the building is so sophisticated. The building is really mean. I've trained them and now The second paradigm.
Do you think if I plug in my computer for some reason it would help? I have no idea. Probably not, right?
No, I don't think it's a problem with the
Yeah. Oh, but it's on now. Okay.
Yeah.
Thanks, Larry.
I don't know.
Okay.
You make all join when we can look at 100 days, you can return all of it.
Go ahead.
There's a question for the organizers. I don't know.
We can join here and can see and read the first page.
Yeah, probably.
Okay, we have the slides back on.
Okay. Yeah. Okay, so the next point that I was alluding to before is that in general, this matrix DFI itself is not guaranteed to be positive definite. Positive definite means that it has only positive definite eigenvalues. That's a much stronger condition than that saying that its determinant is positive definite. So in a lot of models, hopefully we can write this determinant D as a product over two smaller determinants. And then you can, since they're positive definite determinants, you can write this as that D tilde dagger, or D tilde is some kind of, for example, a spin resolved fermion determinant, like in the Hubbard model, or maybe a flavor resolved fermion determinant, like in other models. This is a case that happens frequently, actually more frequently than you think in these sign problem free models. And if not, if that's not the case, then actually you can always bite the bullet and write any positive definite determinant as the determinant of the square root of D dagger, where D dagger is always going to be positive definite, and then you just need to compute the square root in some fashion, which adds some cost. And I'll talk more about this in day 2. Or if the physics allows for it, you can just double the number of fermions. If you square this guy, then it's always you can always write it again as a determinant of D dagger. And if you don't care that the number of fermions is doubled, for example, if you're studying some critical points and you don't really expect the physics to be altered significantly, then you can do this. So actually, the examples that I'll show from our papers, we do this because we really don't care for the physics that we're after. It doesn't make a difference. But in general, this is important to know. Okay, so that's step number 0. So then basically what you do is you rewrite the observable that you have, which is an integral over this Hubbard-Stojanovic field. And then the determinant you rewrite like this. Okay, but then the point is that you don't have to, for every MCMC configuration of this Hubbard-Stojanovic field phi, you don't need to compute this guy to death. You can rewrite this as a joint probability distribution and sample this phi and var phi simultaneously, which means in particular that what you can do is you can alternate between drawing one sample of phi and one sample of var phi, or generically n samples of phi and m samples of var phi. It's up to you. If you make a silly choice, it will just increase your autocorrelation time. But what we found is that just the simple 1 and 1 works fine, and we didn't try anything else. But you're free to do so. Then it's the question of how do you draw these samples? So the two fields are updated very differently, largely because if you look at this var phi, it's just a free theory with respect to that. So this guy you can draw samples from that by simply drawing, for example, a chi from a uniform multidimensional Gaussian and then multiplying that chi by this D matrix, and that will give you a sample var phi from this distribution, this part of the distribution here. Okay, so if phi, your Hubbard-Stojanovic field, is fixed, you do that, and then you update your var phi. But to generate a sample of phi, you need to use Markov chain Monte Carlo because, of course, this distribution is not at all Gaussian, and that's where we're going to use called hybrid Monte Carlo sampling. And of course, we didn't invent this type of sampling. This is the standard method.
So we have had just suggestions to take care of it. One is everyone here logs into Zoom. And the second is we move to the other one. But I will not move now because of the alarm interruption. So what about to just go everyone to Zoom and that's it? And then I don't care about the projector.
Can I still use the projector? All right. It's easier for me. Right. Also, I think we have something on chat.
What did you put on? I don't think it's just what you said.
Okay. Yeah. Okay. There's something on chat. Should I read it or? Okay. 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 Yeah. So this is like I said, this is the standard method of choice in Lattice QCD, and they have their own tricks and that differ substantially from ours. Yeah, but the basics for them it was very successful, and that's all can be. So this is the first paper that I think does this, Duane et al. Paper. Okay, so now what is this hybrid Monte Carlo sampling of this var5 field? Okay, so it starts like this. If you have some generic, so you have some expectation value, some operator O, as before. Now we're always free to add this additional field pi, which we're going to call a conjugate momentum. And the reason why we do so is that we introduce it like this. So it's just some reverse Gaussian integration with this matrix in the middle here called M, which we're going to call the metric. Sometimes it's called the mass matrix. And we're always free to add this such an auxiliary field. But now what this allows us is that pi here looks very much like a conjugate momentum to phi, in that it looks like a kinetic energy, and the rest of the integral looks like a potential energy. Remember here, var phi is fixed, and we're updating phi. So now what we're going to do is we're going to update pi and phi together. So in other words, so we draw a sample from pi according to this distribution, and then we update them in the following fashion. So since this looks like a Hamiltonian system, we're now going to update them both using the Hamilton-Jacobi equations. This tells us in some ODE that tells us how to update these variables in a way that keeps what's called the energy along equal energy contours according to this fancy H, which acts like a Hamiltonian. And so these equations are given as follows. So d phi ds is the integral, the derivative with respect to pi, which is straightforward, and pi is updated with the partial with respect to phi, which is not straightforward. It's just this depends on this integral here. And then we're going to do that, and then this update is going to take us along one of the equal energy contours along some distance, and then we're going to say, okay, stop, and then we're going to drop phi. Okay, and that's going to be our new update. And then we're going to update again. So then we're going to draw an additional sample from pi according to this distribution, flow, and then project back down, meaning just take the phi component. So this flow, according to this gradient flow, guarantees efficient updates in high dimensional spaces. And there's even some mathematical results from statistics that say that, which I'll talk about, I guess, in a second, in the next slide. Yeah. So, however, so that would be very nice. That would give you some way to update. However, the story is not complete because in practice, we always need to discretize our flow equations on a computer or in any real life. And the way to do that is you need to choose a discretized integrator that's symplectic. So symplectic. So one of the properties of it being symplectic is that it obeys time reversal and it preserves the phase space volume element. Okay. So before I explain what that means, I'll just give one like simple example. This is the one that is most commonly used. This is the simplest symplectic integrator, which is called the leapfrog integrator. So what you do is you first you update your phi field according to so you choose some discretization, which is the step size. You call that epsilon. And then, so you alternate between updating phi and pi in steps of this epsilon. But you do this in this particular interleaving way, having first updated half step for phi, and then at the end, you correct for this half step. And there are other choices that you can make for how exactly to write down your leapfrog integrator, but they all look roughly like this. Okay, and so this is just the simplest thing that we use and that lots of other people use, and yeah, it's pretty good. So what does this mean if that your discretized integrator is symplectic and it preserves this phase space volume element? Well, what it means is that even though, so if this is here, the red here is the equal energy contour, and the green is your actual discretized path, what this means is that since the phase space volume element is preserved, you can't, the flow is kind of incompressible. It's like you're always sampling some Hamiltonian system that's very close to yours. And so you're always flowing along some equal energy contours that are approximately this. And since basically you can't squish it very much, otherwise you would change the phase space volume. And so this kind of guarantees that you will almost always not stray very far away from this equal energy contour. It's like a way of making sure that you stay on course. But you will stray a little bit, and then at the end, to ensure that you satisfy detailed balance, you can correct this this step. Sorry, this should be molecular dynamics. So this flow is also known as molecular dynamics. You can correct its molecular dynamics update step with this Metropolis Hastings accept reject. So notice that in this acceptance probability here, the updates, the forward in time and backward in time updates cancel because this update obeys time reversal. And so what you're left is just comparing the value of the Hamiltonian at the beginning of the trajectory and at the end. So it's a very simple acceptance probability. And this gives you your updates. So that's basically all of HMC sampling. And like I said before, there are some theorems from statistics about how this is, if you're doing Monte Carlo, this is like the most efficient thing to do in high dimensions, which is promising. I can't really speak to that very much, but anyways, we see that it does for us work well. I don't know, like I can't really speak about this result much because I don't know its rigor or anything like that. I just
Okay, so I won't have it.
Yeah, I was quoted this result,
Quoting the result,
but I did not. I don't really understand the proof or anything, obviously. So yeah. But it just it's like motivation to try, I guess, was the point. That okay, somebody tells you from stats that this is provably very, very good, and so okay, fine. Like, yeah.
Please once more explain why the fact that it's symplectic and incompressible, that necessarily implies that it would not go too far away, because I could imagine that it maintains the volume and just takes another trajectory there. It's filled up.
Maintains the volume, basically like the volume enclosed by the equal energy contour cannot change.
Yeah.
So you need to kind of reshuffle to a trajectory that's you can't like compress. Let's say your equal energy contour is like some ellipse.
Yeah.
And you can't compress the volume of this ellipse, right? So you can only kind of deform it a little bit and rotate it, stuff like that. but you can't change its volume. So what that means is that if you don't take steps that are too large, you should always stay close to the previous
main trajectory,
ellipse. Yeah. In other words, you're always solving a Hamiltonian system, some Hamiltonian system that's close to the one that
You're basically saying that the errors you make you're basically then saying that the errors you make due to your discretization, they don't kind of blow up and you stay in the sort of
most of the time. It does happen sometimes, apparently, that you blow up, but those cases are, from what I understand, pathological. Like if the curvature is absurdly high or something. Sorry?
Okay. Peter, wait for
Okay. So I'll just keep talking, I guess.
Any more questions while we're waiting for the beamer?
Actually, it's a great method to promote questions.
Yeah.
Very sorry, the responsible people for the beamer wake up at 9 o'clock. So now I can promise.
So it's probably time to take about 5 minutes.
Say I didn't.
Okay. So, but should I just keep talking, I guess?
Yeah, I guess in 5 seconds it should be back on. Yeah, there it is.
Okay.
This one is new. What else? Any interesting questions we could ask? Yeah, right.
Did you try some higher order integrator for leapfrog, basically beyond the second order, like fifth, seventh order, something like this?
No, you can try higher order. I guess it will do. Yeah, you might be able to get away with a larger epsilon, I guess.
Yeah, but you need more work to make the update.
Yeah, but you have to pay for it.
In my experience, it actually strangely enough compensates each other. So
okay, yeah.
So but you didn't.
We didn't try. Yeah. So.
Yeah. Thank you.
Okay. Should I keep going?
Yeah, probably.
Okay. Okay. So I'll keep going. Okay. So now I'll talk about the efficiency of sampling and our auto-tuning procedure. So we'll just go over the HMC hyperparameters. Yeah. Okay, so the HMC, as formulated with the discretized integrator, it has 3 what I'm going to call hyperparameters, which are parameters of the method. So these 3 are the integrator step size, epsilon, the number of integrator steps that you take, and L for leapfrog. So remember that the product of these 2 gives you the length of the trajectory. And the metric M. So the metric M is this matrix that you are always free to choose to be whatever you want. So an optimal choice of these will make the algorithm extremely efficient in high dimensions, as promised, by traversing what's called the typical set of the distribution very quickly. But a poor choice of these can reduce the sampling down to a random walk. And so you'll lose all the things that you were trying to gain. And the key to performance is a good choice of these hyperparameters for every problem, every system size, every set of parameter values. And so therefore, these hyperparameters need to be auto-tuned. which means that you don't want to spend time tuning them on your own. So I'll go through our procedure for auto-tuning these, yeah. So our goal, first of all, so how do you tune the step size epsilon? So when you think about epsilon, you want to choose your step size to be as large as possible without sabotaging the acceptance rate. In other words, you want to take as big of steps as you possibly can to get the furthest away from your initial configuration. But at the same time, if you take epsilon to be too large, then the accept reject will just always reject it. You'll stray too far away from the contour. And so one simple and cheap strategy of many that are out there, but the one that we use is the simplest. So basically, you keep increasing epsilon until the probability of accepting one big jump out of 2 attempts, as long as the probability of accepting one big jump of size epsilon out of 2 attempts is larger or equal to the probability of accepting 2 smaller jumps, so one trajectory consisting of 2 half steps, like this. So basically, you always want to do this because this is twice as much work. So as long as the probability of accepting it is larger, then you want to keep epsilon the same. But if the probability of accepting it is smaller, then you're better off doing the 2 steps. And so that's our criteria. And then when you formulate that in numbers, so you get this equation, and then you just like literally, so you measure the probability of these jumps, 1 step of epsilon, 1 of epsilon over 2, and you compare their values. And as long as so you increase epsilon until this inequality starts to become true, and then if it's true, then you decrease epsilon.
So you do that during your Monte Carlo run, or do you just do it during warm up and you have fixed epsilon for your Monte Carlo?
Sorry, I should have prefaced all this that all these guys, all of these hyperparameters are tuned in the warm up.
Okay.
Yeah.
During the sampling, you're probably exploring different regions of configuration space.
Yeah.
How many samples do I have to take, and do I have to be sure that I'm past the warm-up time so that I have a good estimate of the acceptance probabilities for the 2 steps?
So, yeah, so these acceptance probabilities, we keep a very short running average of them. So they're computed over like a few Markov chain steps, like 5 or 10.
Mm-hmm.
And then, of course, that probability value might change if you're in different parts of the configuration space. But yeah, we don't really worry about that. We compute it so frequently during the warm-up that we just kind of whatever value it is at the time is what we use to change to change epsilon.
Okay.
Yeah. So epsilon, of course, fluctuates. So in general, epsilon, as you track how it changes, the warm-up is like 1,000 iterations or something like that, and you update. You measure this probabilities for epsilon, you update it every 5 or 10 iterations. And you can see that it kind of is jittery, but that it always has a trend.
Okay, thanks.
Okay, so just as a side note, this is not probably the best thing to do. The best thing maybe is using this dual averaging technique. So there's something called STAN. So it's the reference for it is here. It's this, as far as I understand, actual programming language, but it's based around hybrid Monte Carlo, and they have a whole. It's a statistics. It's something in the statistics community, and they have a whole documentation about how they do their optimization in the warm-up, and we follow something kind of similar. So in the STAN manual, you can see details about dual averaging. Dual averaging is a name for a different way to keep track of this step size and to increase or decrease it. Yeah, I'm not going to talk about it at all. It's more sophisticated, but we don't use it. Okay, yeah, and so in this acceptance probability, of these little jumps is it's computed with some fixed number of so we just keep track of this acceptance probability over a few iterations to have some estimate over it. And we just keep maintain a running average of these two probabilities for some recent history, and then we change epsilon every few steps, like I was telling Johannes. So this step is very cheap, and so we do it frequently. So we're constantly changing the step size in our update scheme. And then there's also the number of steps, which are called NL. And the goal with NL is that we want to choose it to be as small as possible, because this NL is what enters linearly into the cost of your algorithm. It's the number of expensive computations that you have to do. So you want to make it as small as possible without paying for it with an increased autocorrelation time, because then you'll just lose what you gained. And a general strategy for this is to maximize what's called the expected squared jump distance. So what this is just the expectation value of so expected squared jump distance for some as a function of n, like the number of steps that you're jumping, for a fixed step size epsilon, is just the expectation value of the distance that you have traveled, okay, at that n, times the probability of being accepted at that distance. Okay, so that curve will generally follow some structure like this. It will be very small in the beginning because the distance that you traveled is small, and also it will be small very far away because the probability of accepting very far away is going to be small. So we'll have some peak. It'll have some peak at what I'm going to call n max, and that's what you want. That's the n that you want to choose. And importantly, it's important to remember just that the distance here that we compute is defined with respect to the metrics. That's why this m is called a metric. It warps your space and it keeps track of distances. So you need to remember to include it in the definition of distance. Okay. So in our warm-up phase, when we're optimizing, again, so this is some average, and you need here some probabilities. So you need to keep track of this of the acceptance probability at these steps. So you keep track of this over some fixed over some recent Monte Carlo history, and then you change this number number of steps NL some every fixed number of Markov chain steps. Since this is the most expensive thing to update, we do this the least frequently. Okay. And also, just for something that we do, searching for this NL is expensive. So you want to be conservative. So you don't need to search, from 0 to 1 million. You can search within some bounds set by your previous NL that you had. So maybe, up to like 1.5 times the previous one. And again, this is not the best thing to do. The stats community has been hard at work inventing new things. So this thing is from I think 10 or 15 years ago now. So a better way for auto-tuning NL, for auto-selecting it, actually, is this thing called the no U-turn sampler, abbreviated as NUTS, invented by in this paper from 2014. That's just what it's called. 2014 by Hoffman and Gelman, and it's what's used in this stand package, and it's definitely the best thing to do. So yeah, we're also working slowly on using this and implementing this to rather than this expected squared jump distance. But at the moment, this is what we use, and it even though it's expensive, it does work very well. Yeah, so that's the number of steps L. Okay, And then the last thing is the metric, M. So what's the point of the metric? That's I guess first important thing to understand before you think about like why you would need to change it. So in HMC, the order of magnitude of the step size is actually limited by the eigenvalue of the covariance matrix of your distribution, phi. So if this guy is extremely poorly conditioned, it has some very, very small eigenvalue. This the normalized version, by the way. Then compared to 1, then you're going to be forced to take very small step sizes. And when you're near criticality, the covariance matrix will actually be very singular. So what this means is that if you're studying a sign problem-free model of a theory that goes through some phase transition, you will necessarily encounter this problem where your step size will start to shrink. So things will become less efficient. And to combat this, we need to choose the metric carefully. And why is that? It's because that if we choose the metric to be exactly the inverse of this covariance, the covariance of this distribution, in other words, if you choose the M inverse to be sigma here, it will rescale.
A question?
Yes.
So why does sigma have to become singular at it depends on the choice of your variables. I mean, you're working with, you have in mind that you have some type of physical field, which is the Hubbard-Satonovich. But if you are in a Hubbard-Satonovich world, then your phi does not necessarily have to couple to the low energy modes.
Yeah, if your phi itself is not like the order parameter,
then it's okay.
Then then it's okay. Sure.
Or not, right?
Yeah, that's okay.
Right. We just want to check.
Yeah, yes.
Good.
So sorry, so I'm thinking more of the example where your Hubbard-Satonovich field is exactly the order parameter of every theory. But of course, if you don't know the order parameter in the first place, you just have some random Hubbard-Satonovich field, then it won't be the case. But yeah, of course, it depends on how on the properties of this HS field. But so in the cases that we're interested in, it's going to be very singular. And so, yeah, so when you choose an M inverse, that's exactly this covariance of this distribution, it will rescale the effective covariance matrix to that of the identity. In other words, the metric warps the energy levels in phase space. So the perfect metric will make them uniform and reduce their curvature. So in other words, if you look at your equal energy contours, they might have some very oblong shape. And then you're going to be limited, the step size that you're going to be limited by is going to be on the order of the width of this ellipse, roughly speaking. And so what your metric will do is it will actually just reshape this guy to a uniform energy level, and that will allow you to take larger step sizes. So you really want to do this if you can. This is the figure on the right is, yeah.
Okay, unfortunately, we don't see the figure because it would be about the figure. So you, if I understand correctly, you want to deform the contour to be circles, essentially.
Yes.
Right.
Yes.
But you also want that if you think about these circles in like eigenmodes of your auxiliary fields or your Hubbard-Satonovich fields or whatever fields you have, do you want the radius of the circle to be uniform as well? Because if I want to avoid large curvature, right?
Yes.
So if I have a very small circle, I have large curvature. If I have a very large circle, I don't have that large of a curvature.
But I think that's normalized. So once it's the size of the circles is fixed once you.
Okay.
Yeah.
So you generate essentially circles of unit radius.
Yes, exactly. So that's another way of saying that the here the effective covariance matrix will be identity. So exactly one.
Peter?
Yeah.
To fix the beamer issue, we would do 10 minutes of break.
You have to do something, right? It's not very nice. I suggest that we just take a 10-minute break, there's coffee.
So let's see till 9:30 as the way it looks, huh?
That's how it is, sorry.
No problem. No problem.
We'll somehow come.
Okay.
German technology, all right?
Should I stop share or something? Or should we just leave it like that? Huh?
It's best to keep it like that.
Okay.
It turns off every 5 minutes.
Yeah.
Of the time.
Ah, okay.
If you want to, we can grab a coffee.
Yeah. Yeah.
So these energy controls will have different levels.
Sorry, 1 second. Jonas, should I just take this off for a second?
Oh, yeah, you can mute it.
Yeah, everything.
remember your mic?
Oh, okay. Well, I guess we'll
Thank you.
And we will continue in round about 1 minute. Peter, did you go into, so you didn't try anything else than leapfrog for integration?
Yeah.
They had a publication in 2019 where they optimized the energy error for the acceptance rate. Alternate method. They work pretty well in my experience. So that you get a better acceptance rate with an alternate method.
Really? Okay. So which integrators did they try?
They derived their own, they optimized the Gaussian ensemble, they optimized the parameters of the symplectic integration to give the best.
Okay. That's interesting. Yeah, can you send me this?
Certainly, if you're interested, I mean, it's also I've implemented them for ESS. They also give us speed over there. Johannes has used them. I consider them pretty reliable methods.
Okay. Good to know. Thanks a lot. Okay, thanks so much.
You have the usual.
So I don't know if I can't see any video.
Okay, let's start again. Hey, audience.
I have to share what? This guy? Yes. No.
So we restart the session. Presumably the issues have been fixed and we continue.
Okay. Okay. So, yeah, so like I was saying, what you want to do is you want to choose a metric that's as close as possible to the inverse of this covariance matrix, and that will allow you to choose a larger step size. That's the goal. And so then, how do we actually compute the covariance matrix? Like, this is actually one of the observables that you want in your theory. So it's a bit weird to be asking for this information in the warm-up phase before you even have your data. But actually, as with the other hyperparameters, we can keep a running estimate of this guy. And it turns out that doing so is very advantageous. And then we update it. So we keep a running estimate and we update it at every fixed number of steps. But of course, you still can't collect enough samples to estimate the entire matrix because this thing is, the size of it, the number of entries in it is beta volume squared. So a key simplification is that actually we don't need the entire covariance matrix for the purposes of acceleration, for the purposes of using it as a metric. What we can do is we can use translational symmetry in both space and time. And this allows us to only keep track of the diagonal parts of the Fourier space correlation function. So in other words, if we write sigma in Fourier space, we only care about this object. And this object is now diagonal, and it's just the diagonal. Of course, in the case of additional flavor or spin indices, it's block diagonal with some small block size. But this simplification means that we can estimate the covariance matrix actually in order 1 steps, because each Hubbard-Stojanovic field phi contains the information, as much information as is on the diagonal. So basically, we only need like 32 samples, roughly, to get a good estimate of this. So the running average that we have over like the last 10 Markov chain iterations is actually pretty good. Like it gives us all the information that we want. It's just that, of course, we're not yet sampling as efficiently as we want. So it won't be perfect calculation. But in the warm-up step, it will give you something. So this estimate is, again, cheap. It's linear up to logarithms, and it's done, again, more frequently. And
your field, it's tau dependent. You do a Matsubara transformation, Fourier transformation of this noisy field, and you just calculate the diagonal, and you impose and this is so you impose that it's diagonal positive definite matrix.
Yeah, it is always positive definite.
But not for a sound. Not if you don't do something. If you have if I calculate the covariance matrix, in a sloppy way, it won't be because of the errors. It won't be positive definite.
Yeah,
right?
yeah.
So you have to repair this somehow, and that's what you're doing.
Sorry.
Somehow.
So you do have to, yes, you do have to correct this.
And that's what you're doing because you're just sampling what you're sampling now here, if you really sample this is by definition positive, right?
Huh? It's by definition what?
Positive.
Yes.
Even for every sample, right?
Yes.
Okay, good.
When you do not have translational symmetry, then.
So amazingly, when you don't have translation symmetry, this still works. Even though.
Why?
And the reason for it is that I'll talk later about the other example, but we applied this to a model with quench disorder. And actually the quench disorder that we have is pretty large, but it's not, as long as you don't have infinite disorder variance, it seems to work. So first of all, you always still have translational symmetry in the time direction. But then also, what happens is, okay, of course it depends a lot on the physics, but in our model, basically, the small k modes are not translationally invariant, but the larger k modes are. So if you compute this sigma of k1, k2, this is k1, k2. When k1 is 0, then indeed there are largish off-diagonal components, depending on the parameter of phase space on the physical parameter that you look at. But then for any k2 not equal to 0, it's not that large. And so anyways, the point is that we're only computing the diagonal part, and there might be other non-zero elements, but they are not very many, and regardless, they are small. So even though you don't get this exactly as it's not as well computed as it would be in a translationally invariant system, because in that system, all the off-diagonal elements would really be basically exactly 0. Even though that's the case, it's still good enough to give you to do what you want in terms of the metric.
Okay, so I say I'm worrying about the reversibility by using this kind of trick. And actually, you use the covariance matrix in one direction. So it does not, it may not agree with the covariance matrix when you calculate it from in the reverse order. And and actually, I also have some the same question about your adaptive scaling of the step size of molecular dynamics. Actually, your conditioning is only one direction.
Yeah, of course. So in practice, we only do updates in one direction.
But it breaks the reversibility.
If you were to do the update in the actual opposite order, and then recompute everything, then yes, you would get potentially different values.
Right.
But we don't do that, right? In accept reject, it's just you don't actually go forward and backwards. You just put the probability of going forward and backwards, and we do it. When we put that, it's the same exact. We use the same values for the forward and backwards.
How is the same value in capital?
Yes, this is in warm up.
Okay.
Yeah. So okay. So this is done in warm up. Yeah. So in actual, so this is in the warm up. When you compute, when you collect data, you stop changing everything. It's fixed.
Maybe we can discuss it later. But actually, and this is why Alicia introduced how you click. to complete the reverse ordering time, right? And
Okay.
Sorry. Yeah, it's okay. Yeah. Yeah.
Yeah, and my question are simpler. So I thought this kind of like a chicken and egg problem, like you wanted the matrix to help you to sample, but you have to generate the matrix on the way.
Yeah.
So yeah, in reality, when you do the simulations, each parameter, physical parameter, I mean, let's say you go scan through the critical point, each parameter you have to determine this for each physical parameter.
Yes. So
yeah.
Sorry. So all of this is done with the physical parameters of the Hamiltonian fixed, right? I'm doing one simulation where the Hamiltonian of the physical system is fixed. Is that what you're saying?
But let's say you change to another physical parameter.
Yes.
You have to determine this matrix again.
Correct.
I see.
Yes. So the warm-up, so every time that you have, this is the whole point, is that you want to study, let's say, your physical system at many different parameter values, but also many different system sizes and temperatures.
Yes.
So each time you would have to go in, if you want your sampling to be efficient, you would have to go in and figure out what is the optimal value. Instead of doing this, we just want to run the warm-up that will do everything for you without thinking for each parameter value.
Yeah. So compare with the real, like see the heavy duty simulation. Compare with the real simulation, this kind of effort in terms of, let's say, CPU hours is negligible or actually substantial?
So you're asking about the amount of time we spend in warm-up compared to the amount of time we spend in sampling. It's some fraction of it. You want to compare, I guess, the total amount of time that you spend in warm-up to the amount of time that it takes you to get one effective sample. For us, it's like maybe I don't know. I can throw some numbers out there, but the warm-up time is not zero. It is significant.
I see.
Yeah. I see. Maybe like 10. Maybe like the warm-up time. Maybe the warm-up time is like, I want to say 10 times the amount for one effective sample or something like that in the worst case scenario for like the largest systems that we do near criticality at the lowest temperatures. Yeah.
So the same question as Ziyang, do you keep your configurations as gold? This is very important for you. You put it, or you just throw them away and then you warm up at every run?
So
and then that will answer your question, right? I mean, if you keep them, that means they're really important for you, like the QCD people, I suppose.
So you don't actually need you don't need to keep track of the configurations in the warm-up. You just use them to compute the various things like the covariance matrix, the estimate of covariance matrix, and the acceptance probabilities, and then you throw them away. Yeah. So you don't actually need them beyond where you're at in the warm-up. Yeah. So.
Can I ask?
Yes.
Quick question. Yeah. So hi. Just a small question about this assumption on the covariance matrix. If, say, you have a system with a significant disorder, and you still assume this kind of statistical transition invariance, is there a danger that you kind of assume to have this statistical transition invariance, but in reality you might encounter some localization or some strong disorder regime? Will this be missed by this assumption on the covariance matrix?
So yeah, I think this question was already asked, but the answer is no. Like, if you have disorder, then you have off-diagonal components of this covariance matrix, and you're just neglecting them. So how good of an approximation that is case dependent. So for the system that we studied, even though we were in a pretty strongish disorder regime, we saw that, and there were some off-diagonal elements that we could compute later. We saw that the metric, as approximated by this diagonal and momentum space form, it worked very well.
So, but if you now, so I'm worried about this choice sampling only, the kind of statistical translation invariant part of the phase space and not
No. You don't sample the statistical. No. So there's no danger, right? If you choose a bad metric, it will just mean that you will sample less efficiently. It will not break any kind of ergodicity.
Okay, okay. Yes.
Yeah. So it's a danger in being inefficient, but not in being incorrect. So yeah, so there's better things that you can do to decrease the amount of warm-up, and that's so this Stan package, they work hard on like what's the quickest way that we can warm up. And so this no U-turn sampler is a very good thing, and this dual averaging for epsilon is good. But yeah, we find that. So I'll show the system sizes and everything that we can reach. And so for us, even though the warm-up takes some time, it's still the total amount of time spent in overall, compute is not that large for the data that you get. So yeah, so this so then all three of those things are tuned. And this is exactly how, so all three hyperparameters are tuned automatically and in some initial warm-up phase. And so the way that this is done exactly is that there's some thermalization or burn-in to get you to the typical set, which happens with all MCMC calculations. And then before collecting data, you want to spend some time optimizing these guys. And again, you're not collecting data because, yeah, as was pointed out, if you're changing these inside here in some non-random way, then actually it's not even, you can't collect statistics yet. You can't collect data yet. So there'll be some window, so some big window, one full iteration of all the hyperparameters ends when you change the number of leapfrog steps here, NL. And this is because this is the most expensive one, and you want to do this the least frequently. And then you compute. Well, what we do is we compute epsilon many times, and we like change every 5 or 10 iterations. The metric has changed every however many iterations, like 20. And then the number of leapfrog is changed every 100 or something like that. And then you repeat this whole cycle however many times it takes for all of these hyperparameters to stop changing. Okay, so the epsilon and leap are just numbers, and the metric you can compare the old metric to the new metric and just compare the norm and see that it's smaller relative norm than some cutoff that you set.
Well, I think so.
So, okay, so you make this kind of auto tuning only before taking samples.
Yes, yes.
Okay, okay, now I understand. Okay, thank you.
Yeah, if you were, yeah. Okay, so those interested, so of course, yeah, so first of all, so in practice, for those interested, the number of these loops, full loops that you need to do ends up being like 3 or 5 or something like that generically, even at criticality. And yeah, of course, there are hyperparameters, which are like, you have to choose the width of these bars, etc. So there is some playing around initially with setting up this procedure, but then once you try something that works, then it just generically kind of works in the rest of the phase diagram and for all the system sizes, blah, blah. And then you collect data.
How do you test for convergence? Like, to which accuracy are the parameters supposed to be fixed?
That's not really well defined, but we choose. So what we do is, I forget. I think we ask that nleap stops changing within like less than 10%.
Okay.
And the norm of the metric stops changing to within some point 1% or 3%, something like that.
Okay.
You just choose something that you're satisfied with. Yeah.
Well,
There's no real answer. I'm sorry.
No, yeah, I get that there is no precise answer, but I mean, in practice, this is a number that you will have. Yeah, the ballpark is interesting, and in practice, you will have to set a number. And depending on what you have, sometimes you need 3 cycles for convergence or 30 cycles for convergence.
Yeah, yeah.
So Thanks.
No, if you set it to be absurdly small, then yeah. So like I said, if it's like 3 to 5 cycles, that I think should be a ballpark for you.
Okay.
Yeah, that's good. And yeah, so to note, this auto tuning can also be done with hybrid Monte Carlo with exact forces, which I think Johannes talked about. Not really. Okay. Yeah. Okay. So that's what we do. Okay. And then once beyond the warm-up phase, so once the optimal hyperparameters are found for your one master seed, for the one Markov MCMC chain, they can actually be recycled for other chains. You don't need to redo this. So you can run one walker, and then all the other walkers, you can set them after you've computed the warm-up and you recycle. So then you don't need to run the warm-up anymore. You just run a thermalization again. Maybe you want to make it slightly larger or something, just to be safe for you. But then you start off with basically the optimal values that you pre-computed. And then you collect the data. And so amazingly, this works even with disorder. So if you have, like, let's say 10 different disorder configurations, for each of which you run a walker, then you compute the optimal hyperparameter values for one disorder configuration. It will then work the far majority of the time for other disorder configurations. Yeah.
I have a question to your comment that it sounded like you're proposing to do the how did you call it, hyperparameter optimization pretty much with a single walker or on a single core.
Yeah.
Instead of for all the cores that you might want to use for the actual data collection. The question that I would have is, sure, you use less cores during the optimization, but wouldn't you profit from the multiple cores by getting more reliable estimates for the self-energy, or for like all the other statistical samples, the sigma ij that you use for the matrix optimization? Because they are all measured from statistical samples, right?
Yeah, I'm just talking about a walker, like one walker. So if you use some MPI to do a bunch of cores, and then yeah, I mean, of course, you could do that. You could have a bunch of walkers that are all doing a warm-up together in some sense by using all the statistics for a better estimate of all these things that you want in the warm-up. That's true. Yeah, you could do that. But I'm just saying that that's maybe you don't have so much resources. So what you want to do is you want to minimize your CPU time or GPU time. So then something like this makes sense, because like I was saying, that the warm-up, it takes some fraction, right? It's not zero. It takes some fraction. So maybe you don't want to repeat that 10 times or 20 times.
And it sounds like you don't profit all that much if you average the input for the auto tuning over many cores. That it's like not a big advantage to run this in parallel.
No, we haven't tried.
Okay.
Yeah, I don't know.
Okay.
No, of course, yeah.
So you were saying that this works for all kind of disorder, but even if you have, for example, magnetic impurities or charge impurities, that you can just reuse the same warm-up?
So the exact disorder theory that we tried this on, is where I'll show it, but a theory where you have some Yukawa interaction between your Hubbard-Srutonovich and your fermions, and that guy is actually fully disordered in space, some quench disordered space. So it's like you have a site-dependent interaction between your electron and your boson field. And in that case, there's some structure, there's some non-translationally invariant structure that comes about from this quench disorder. And it was, even though it plays a significant role in the physics, it was not enough to kill basically the optimal parameters between disorder configurations in the warm-up.
Yeah, but it's okay.
I don't have a deep answer as to why this is. It just, yeah.
Thanks.
Okay. So I have no idea how I'm doing on time because everything got.
Should be 10 before 10.
Yeah, it's yeah. So.
I think that at least 15 or 20 minutes.
Okay. Okay. So. Right. So. Yeah. So that brings us to the data collection. Then when you collect the data, what is your final cost? What is your computational cost that you have incurred? So the total cost of this HMC is proportional to basically your autocorrelation time times the NL. So NL is the number of leapfrog steps, or the number of steps that you take in your integrator, and that's like the number of operations they need to do per update. So this gives you the cost of one effective sample, and this is addressed. Reducing this cost is what's addressed with this auto-tuning in our paper. And then, of course, all this is multiplied by the cost of a single expensive operation, which here is a matrix inversion. Okay, and this is addressed in our forthcoming papers with what's called preconditioners, and I'll explain that later. So the cost of this one effective sample in HMC in general scales like this. It's the scales as beta to the power 1/4 plus Z1 times volume to the power 1/4 plus Z2. So here Z1 and Z2 are exponents of the critical slowing down. So if you have some kind of stickiness, like at a critical point or in a critical phase, then these guys can be large. And this matrix inversion is like, it's the cost of solving a linear system of size beta V. And it depends a lot on the implementation, and it can also suffer from critical slowing down. So I'll address that point tomorrow. Yeah.
Okay.
The Z1 and Z2 are just for the one effective sample part, or is it also so
No,
the O beta, your O beta of 1/4 plus Z1, V 1/4 plus Z2, that's for the total cost.
No, sorry.
Sorry, I got it wrong, right?
That's a cheat. I'm dividing it up like this. So Z1 and Z2, yes, should be parts of the total cost, because there are cost of critical slowing down, which comes from the matrix inversion.
Exactly, right.
But I'm just writing it in this way to, so I'm writing it in this way to separate out what is the critical slowing down from the sampling.
Right.
Yeah.
Are there some cases where Z1 and Z2 are 0?
Yes, I'll show that in a second.
So is there any case, is there a known case where Z1 and Z2 are different significantly?
I don't know about significantly, but I'll show in this next example where they're different. Yeah.
Thank you.
Okay, so that's the theory. And now I'll just show the example that we've run this to death on. So the theory that we've studied with this method is this spin-fermion model. So yeah, you don't need to know all the details here, but basically you have some fermions, and they have a spin index and band index. And they have some Fermi surfaces that are shown here in this figure. The two different bands are the two different colors. And then they interact with some boson, phi, which is your Hubbard-Srutonovich field. So this boson is some 3-component order parameter for a spin density wave transition. And with this boson, we endow it with its own dynamics, just to yeah, kind of for symmetry reasons, just because it will be generated. So we want to see what the propagator will be modified to from the, let's say, local form, local in space and time form. So these C, U, and lambda are boson parameters. So this lambda here is what tunes this transition to a symmetry, so to a SDW symmetry breaking phase. And so, like I was saying on the first slide, sometimes you have to just double the number. Sometimes you can double the number of your fermionic degrees of freedom to make this pseudofermion trick viable. And so that's what we do here, where this J index is between 1 and 2, where in an ideal scenario, you would want to study this n f equals 1. And so here, this G is the Yukawa coupling between this boson and fermion. So the psi here are the electrons, by the way. And this Yukawa coupling consists of both translational invariant part and spatially varying part, G prime of R. And this G prime of R will have a variance, which we also call G prime. And we study the two different cases. One, which is the clean version, where G prime is 0, and the other one where G is 0, so the fully disordered case. So here's a schematic picture of the model, the two lattices, the two bands interacting with the boson, but at each site it might be a different value. Yes. Okay.
10 minutes? 10 before 10? You told me 10 minutes.
Okay. 7. Okay. So yeah, just I'll flash this. It's not, I guess, super relevant to the method, but the point that I'm trying to make here is that the physics of these models, regardless of whether you're studying the clean case or the fully disordered case, there is always a region of criticality. So here in the clean case, there's a point, a quantum critical point, and in the disordered case, there's a quantum critical phase. But in both cases, you will observe the typical problems of critical slowing down. You should observe them in the vicinity of these points or phases, because yeah, so phi here is exactly the boson that is going critical. So as pointed out, it's not always the case, but here it is. So this problem should be difficult in terms of sampling exactly in these regions. Okay, so here's just kind of a quick flash of some observable, just to show that you know, what we can do with the method. So here's an example for the clean model at criticality. We can go up to system size 80 and temperature 20, and system size 20 and temperature 80. So we can address kind of both limits. We didn't take the two limits together. So here, for example, for this 80 by 80 system, you can see we can compute some fermionic observable, like occupation number, and yeah, it's pretty good. We can zoom in and get very fine features in momentum space of what's called, for example, hotspot physics. But in terms of the actual performance of the method for these models, so here again for the clean case, I'll show some results for the disordered case tomorrow. But for the clean case, you can see that so again, your effective sample cost is this, and what we get is that Z1 is 0.5 and Z2 is 0. Okay, so the critical slowing down that we have in space and in the spatial size is 0, and Z1 is different, it's 0.5. So is, yeah, 0.5, I guess, is somewhat different from 0. I don't know, maybe not a lot, but anyways. So that's the scaling that we get. And then, but the cost of a single matrix inversion scales roughly like this, as beta squared times V. So it's linear again in the system size, so we don't have any additional problems there. But in terms of temperature, the beta, it scales beta squared. So that gives an effective total cost per effective sample of this, which is beta to the roughly 2.7, and volume to the power of 5/4. Yes. So in beta, it's worse than BSS.
Because just think about a z equals 1, right? Basically a Lorentz invariant system, which is not the case here, right? Then you have, if you switch beta and volume, you don't care. So BSS is volume to the cubed. No, I'm getting it wrong. I'm sorry. So it is better. Sorry.
Yeah, in volume,
my
it's,
bad, yeah.
in
I
volume,
thought, yeah, it's better. Yeah.
yeah, so in volume, it's much better. Volume in a two-dimensional system is L squared, and this is 5/2, so it's L to the power 2.5, yeah. But of course, in beta, it's worse. But yeah, still, I want to point out that despite the fact that the scaling in beta is not that great, the prefactor is so small that we're able to get to pretty small temperatures, beta 80, for a system size that, at least in the BSS algorithm, some other groups did this and they weren't even able to reach the system size of 20. So yeah, and then in the other limit, yeah, we can go to very large system size. So this is so here I want to point out that the scaling in volume is at the theoretical, I said maximum in V, but actually I guess minimum in V, even at criticality. So this is at the critical point. And what's promised from HMC, regardless of physics or not, is that the best case scenario is V to the 5/4. And this result this prediction of HMC does not say anything about the cost of some matrix inversion or anything like that, just about sampling. So here we can achieve that best case scenario in volume. And here, since this our results here, this is for the first paper, and now we have a lot more sophisticated tech having to do with the matrix inversion, not just using a better preconditioner to improve the scaling with beta, and also the prefactors, but also using like mixed precision conjugate gradient solvers and matrix-free MATVEX. So it should be even faster now. But we're testing this on the disordered case. So yeah, that's the end of day 1.
Thank you for your nice lecture. I guess we can move over to the question session.
So the way how I understood the tuning, or how I understand the tuning of the M matrix from the self-energy of the bosonic field, is you're trying to make it more or less Gaussian. The theory is so that you have these nice circles in which you can integrate.
Yeah.
So if you tune to the critical point, the Gaussian part vanishes, where you start transitioning from the Gaussian potential to the Mexican head potential when you have symmetry breaking.
Yeah.
So what happens when the self-energy sigma that you measure to tune the mass matrix M vanishes, or at least some components of it are vanishing or close to vanishing?
Yeah. So at criticality, yeah, it's very poorly conditioned, but it's not going to vanish for any finite size. But yeah, it's not going to be great. But then the problem will come with the inverted landscape. So there I'll talk about this tomorrow, but there we are seeing some issues related to sampling that we are not sure where exactly they come from, but they probably come from the inverted landscape, and they manifest in some way that I'll discuss tomorrow.
Sorry, maybe a physics question. I'm not sure whether you prepared. Is that I don't know. I mean, I just arrived today. So the question is that at the criticality of your system, have you tried to look at the self-energy, your fermion self-energy? I mean, sit at hotspot, and then for your beta equals to 80 simulation, how the self-energy, imaginary part of self-energy behave as a function of Madhubara frequency?
So we haven't done this for the clean case,
Yeah,
but we did it for the fully disordered case.
right.
I'll show the results tomorrow.
Uh-huh.
But there's no hotspot. It's because the whole Fermi surface
Sure.
is hot. But the punchline is that it's marginal Fermi liquid.
Yeah, so when you say it's marginal Fermi liquid, what do you mean?
I mean that
Uh-huh.
the self-energy as a function of Matsubara frequency fits extremely well
Uh-huh.
to a omega log omega form.
I see.
Actually,
I see.
it's super logarithmic marginal Fermi liquid because
see.
it fits better to omega log omega plus omega log omega squared.
Right, I see. I see.
Yeah.
So in the PSS case, what we did before is that in the clean case
Yeah.
for the icing and XY criticality,
Yes.
you really have to subtract the thermal contribution of the self-energy
Yeah.
to be able to review the quantum power law
Yeah,
or the log you're talking about.
Yeah. So
Yeah.
we worked on this as well.
Yeah.
We had some definition of this quantum self-energy.
Right.
Some non-perturbative definition. That'll be talked about more in the forthcoming paper. But we found that actually we don't need it. Just looking at the self-energy exactly, you could resolve everything at low frequency, at low temperatures. But it wasn't necessary.
Sure. But for the clean case, for this case,
No, for the disordered case.
but disordered.
Yeah.
Okay. But for the clean case, it's
We
not.
didn't check it. And also since we made all these further technical advances, we
Of
have
course.
not returned to the clean case. So I don't know. I can't answer.
Good.
Yeah, but we will do that at some point. But
Sure.
I don't know the answer at the hotspots.
Okay. Yeah.
Yeah.
Thank you.
So you are tuning M matrix at warm-up, but did you try to check whether this choice of M matrix remains optimal after warm-up phase, depending on the place where you in the configuration space for the model? Because maybe you can like travel to some different place in configuration space where this choice of M matrix will not be optimal anymore because like,
Yeah. So what I said was actually cheat because the actual optimal value of this matrix should be the optimal value should be the non-averaged one should be the configuration dependent, just phi I, phi j. And we don't use that. We just use the average one, which we see is good enough. And we definitely don't like try to see like, oh, did we average over only this region of configuration space here to get an estimate of the mass matrix here or a different one? We just aggregate over wherever we are sampling and we don't worry about it. So we didn't, the bottom line is that we did not check this.
Okay,
Yeah.
I see.
I don't know if it would be different or not.
So for this specific problem, you have no zeros of the fermion determinant, or you do? Or
We
you-
have near zeros, but no, we have no exact zeros. No.
How do you know? You can show that? Or you, is it true? I don't see that. I don't.
So the pseudofermion thing would not be well defined, and we do. I guess we would not be able to invert the fermion matrix, right? Every fermion.
But it's near zeros. What does it mean? I mean, near zeros, that means it's
It has a very small. The fermion matrix has a very, very small eigenvalue, but it would not be exactly zero. If it was exactly zero, our conjugate gradient iterative inversion procedure would never converge.
Is there a way to show it?
Yeah, but actually, you can still use this pseudofermion tricks even if you have zeros of determinant, because HMC will automatically push you away from these configurations where you have zero of determinant, so that you will sometimes see that number of iterations explodes. But in principle, if step size in molecular dynamics is small enough, then you will successfully turn away, like you will make like U-turn in the vicinity of
As you're
zero.
approaching a region where it's decreasing, it will turn away. But the question is like, if you run into a literal zero, what will happen? The method will just stop. Because
Well,
a single
on-
inversion will
honestly,
happen.
it's rarely happens even if you have zeros. So the question is, but usually like in QCD, for example, when you introduce some mass storm in Hamiltonian, you can analytically prove that this mass storm lifts all zeros, all zero eigenvalues of fermionic determinants. So
Yeah,
do you have some proof like this?
in like a Hasenbusch mass thing.
Yeah, well, something like this. I
No.
mean, it can be any mass storm which just removes zero modes.
No, we don't have.
You didn't check anything like this.
No, we just, yeah, for the inversion, we just have a preconditioner, but it doesn't, yeah, it doesn't shift the
I understand, but
zeros like that.
this is a bit unrelated precondition. So basically, the claim that you do not have zeros of determinant, it's kind of empirical claim that you simply do
Yes.
not see that the number of CG iterations goes up.
That's correct, yes.
I see. Thanks.
Any questions in the online audience? Any other questions?
Why is there such a difference? Okay, so maybe if I had a Lorentz invariant system again, why would I still expect to have such a big difference between the beta scaling and the volume scaling? I mean, the volume scaling is remarkable. If you have something like Lorentz symmetric, then the beta scaling should be the same. It's not the case here, I understand, but can you argue like that?
Yeah, for Lorentz symmetrical case, indeed, beta scaling and volume scaling are the same.
Also,
Yes, that we checked.
So both
It's basically 1.5 for both volume and temperature.
this is the case both for the sampling efficiency and for the matrix inversion.
Well, this is for sampling efficiency. For matrix inversion, it's a little bit better because sampling efficiency also includes this increase of the correlation time and so on.
Can you separate out the costs? Like I understand that due to the physics, yeah, maybe the sampling efficiency is the same, but the matrix still has some.
Okay, maybe it's just a question of terminology. In sampling efficiency, I include all additional scalings. Like with increased system size, you sometimes need to increase trajectory length, or like maybe more frequently, you need to decrease the step size in molecular dynamics, so that and this all adds up into scaling, while pure matrix inversion, it's just scaling of one solution, basically. So this 1.5 is for the whole thing, which includes decreasing of step size in molecular dynamics with increased lattice size. For only matrix inversion, I honestly don't remember right now, but it should be something a bit smaller than 1.5, 1.3 maybe, something like that.
Time for one last question. If that is not the case, let's thank Peter again for his lecture. And I kind of suggest, so you have 15 minutes of break. We meet again at 10:30 and we continue on schedule.